Okay, so finally we're ready to put together a bunch of the things that we've been looking at recently and put this into the fundamental theorem of calculus, or commonly known as FTC. All right, so FTC is sometimes looked at as one theorem with two parts or two separate theorems. It doesn't really matter. We're going to look at it as the fundamental theorem of calculus and then the second fundamental theorem of calculus for the other piece of it. So let's start here. So the fundamental theorem of calculus. This says, if a function f is continuous on the closed interval and capital F is an antiderivative of little f on this interval, then to evaluate the definite integral a to b of little f of x dx, all you have to do is do capital F of b minus capital F of a. This is very interesting. So this links up that whole idea of the antiderivative, which is really part of the indefinite integral, and now the definite integral. It says that if you want to evaluate this integral, what you would do is you look for an antiderivative of this and then simply evaluate that antiderivative at b minus the evaluation at a. That provides us with a way of actually evaluating this integral. So that's what I was going to say, is the meaning provides a way for directly evaluating a definite integral. So this means that we don't have to go to some sort of limit of an area. We don't have to go to geometry to figure out a definite integral. As long as we can find an antiderivative at big capital F for little f, then we can do this definite integral by the difference of two function evaluations. Now, that makes it sound very, very nice. It is nice. The difficulty is in often finding that antiderivative. But let's see how it would work in some nice cases and what kind of notation we use. All right, so I've done out this first example already. So let's take a look. If we wanted to integrate from 0 to 1 2x dx. All right, so what we would do is, so look inside here first. We would basically say, there's your constant 2 that's going to stay around. Then if I integrate x, I get x squared over 2. So that's what we would have done if we were just doing an indefinite integral. So for a minute, we're ignoring the 0 and the 1 and just looking at this as some indefinite integral, which we would get by this. Now, instead of doing plus c, what we're going to do is, and commonly put this in brackets, and then note that we're doing 0 to 1. So I'm going to just simplify, crossing out the 2, so we get x squared from 0 to 1. And the fundamental theorem says we evaluate this thing at 1 and subtract the evaluation at 0. So this is x squared at 1, and this is x squared at 0. Obviously, we get 1 minus 0, and that's how we get 1. So that's the whole idea of how we're going to use the fundamental theorem to evaluate definite integrals. Let's take a look at another one here. All right, the integral from -1 to 1 of t squared minus 2 dt. All right, so I would just go here and I'd say, all right, let's do the indefinite integral. Integrate t squared. Well, remember, that was t cubed over 3. Add 1 to the exponent, divide by the new exponent. minus integrate 2, and I would get 2t. So then I'm going to put brackets, -1 to 1. All right, equals. So then I'm going to take everything that's inside, and I'm going to evaluate it at 1, and then subtract the evaluation at -1. So the evaluation at 1 would give me 1/3 minus 2, minus the evaluation at -1 would give me -1/3 plus 2. Okay, so this was evaluate at 1, and this was evaluate at -1. Remember, it's the evaluation at the top minus the bottom. Okay, now all I have to do is simplify that. All right, so 1/3 minus 2 is 1/3 minus 6/3, so that's minus 5/3, minus, and then 1/3, -1/3 plus 2 is -1/3 plus 6/3, so that's a positive 5/3, so I ended up with -10/3. And there's my answer. So that's what this integral is. Let's point out a few things here. Okay, realize that if I did this integral as the integral from -1 to 1 of x squared minus 2 dx, I would still get this answer. Remember that variable in there is a dummy variable in a definite integral. It's not going to change what the value of the integral is. All right, what else? All right, so remember that in order to do this definite integral, I'm first going to basically ignore the fact that it's definite. I'm going to do the indefinite integral, and I don't need a plus c. I don't need any plus constant, because if I had that constant, it would be both in the first evaluation and the second evaluation, and since we're subtracting, it would get subtracted away. So it wouldn't be wrong, but we don't need it. So I have this indefinite integral, which I then evaluate at the top minus the evaluation at the bottom, and then I just calculate it out. All right, how about another one? Integral 0 to pi 1 plus sine x dx. All right. So first, let's just concentrate on integrating 1 plus sine x. All right, that would integrate, 1 integrates to x. Sine x integrates, so sine integrates cosine, but negative cosine, because I have to get on derivative, get back to positive sine. All right, this 0 to pi. Okay, which means I'm going to do it all at pi first. So pi minus cosine pi, and subtract the evaluation at 0 now. 0 minus cosine 0. All right, well, this is pi minus cosine of negative pi, cosine of pi is -1 minus, and I get 0 minus cosine of 0 is 1, so I get a -1 in there. I get pi plus 1 plus 1. I get pi plus 2. There's your answer. All right, about another one. This is problem 4, so that's not part of the problem there. Okay, so what do I do about all of this? Well, I have a couple of ways that I could do this. So what I'm going to see is I have basically the integral 0 to 1, and I have basically a 1/3 times x minus radical x dx, meaning I can take out a 1/3 and do the integral 0 to 1 x minus, and then again to do integrals I'll change that to x to the 1/2. Okay, so I have a 1/3, and now I'm going to again integrate what's inside. X is x squared over 2 minus, all right, x to the 1/2 integrates to x to the add 1, 3/2 over 3/2 or times 2/3, 0 to 1. So I get 1/3. All right, now I'm going to do this whole evaluation at 1 first. So 1/2 minus 2/3, and then subtract the evaluation at 0, which would be 0 minus 0. So we get 1/3. 1/2 minus 2/3 is 3/6 minus 4/6. So I get 1/3 times negative 1/6. So I would get negative 1/18. There we go.